Today we look at how we can make use of this concept of the derivatives to sketch the graph of some functions. And we will be applying it in graphing polynomials as well as rational functions. So at the end of this lesson, you must be able to do a calculus-based analysis of the function and use this as basis for sketching the graph. Okay, let us work with some examples. Our first example will be to do a calculus-based analysis of the properties of the function y is equal to 3x minus x cubed, and then use this to sketch the graph of the function. Now here we are given a polynomial function. Y is equal to 3x minus x cubed. And if you do a calculus-based analysis of the properties of a polynomial function, then this will just be on the location of the critical points, the location of the point of inflection, as well as investigating concavity of the graph at some intervals of x values. So if we proceed now with this, the first thing that we have to do is to locate the critical points. These are points on the graph where y prime is 0. So with y prime equal to 3 minus 3x squared, equating that to 0 will now give us 3 times 1 minus x squared is 0. Or in terms of the product, we have 3 times 1 plus x times 1 minus x equal to 0, which is now used as basis for determining x values for which the product is 0. So the product is 0 when at least one of the factors 1 plus x or 1 minus x is 0. And this will be so at x values of negative 1 and x equal to positive 1. And correspondingly, we have y value of negative 2 and positive 2. These are obtained when we substitute in place of x here the value of negative 1 or positive 1. Okay, so at this point, we have located critical points. Now, we check on where the point of inflection now is. And these are points on the graph where y double prime is 0. And with y double prime equal to negative 6x, that will be 0 when x is 0. And correspondingly, y is equal to 0. Okay, let us now place this result or these values of x in a table where we will be computing value of f prime as well as of f double prime at some given values of x, and conclude as to whether we have a maximum point, a minimum point, or just a point of inflection. So take note that earlier we said the critical points are at x equal to negative 1 and x equal to positive 1, and correspondingly we were able to get value of y or f of x, and that will be at negative 2 and positive 2 respectively. Also from the previous analysis, we have point of inflection located at x equal to 0 where y is equal to 0. Okay, so if you will now work with some intervals of x values to the left and to the right of the critical point or the point of inflection, then we will be able to define the following intervals. X is less than negative 1, that is the region, or this will describe the points to the left of x equal to negative 1, and points to the right of negative 1 but to the left of x equal to 0 would be points where x is greater than negative 1 but less than 0. And for those that are to the right of x equal to 0 but left of x equal to 1, we will have x values of greater than 0 but less than 1. And whenever the point is to the right of x equal to 1, then the x's would always be greater than 1. Okay, so having defined these intervals, okay, with the points or the critical points and the point of inflection, we now look at the sign of f prime and f double prime. Okay, and based on the results of f prime and f double prime, we will now be concluding as to the point being a maximum point, a minimum point, or a point of inflection, as well as also conclude as to whether the graph in a given interval of x value would be increasing concave down or increasing concave up, or it may be the case of it be decreasing but concave up or decreasing concave down. So for x values that are less than -1, f prime of x will be with negative value. Okay, of course, the factor 3 will always be positive, and when x is less than -1, the factor 1 plus x will be negative. So you can make use of a test value, say -2. So 1 minus 2 will be negative, and then the factor 1 minus x will be positive. Say again, with test value of -2, you will have 1 minus -2, that will give you a positive 3. So the first factor is positive, the second factor negative, the third factor positive, and the product of these three factors is noted to be negative. So for any x less than -1, f prime of x would be negative. But f double prime of x, which is defined as -6x, would always be positive. So what can we get out of this result? With f prime of x negative in this particular interval, this will imply that the function is decreasing in this particular interval. Or if we are going to trace the curve, then we will be going downhill. Now with f double prime positive, this will tell us that the curve is concave up. So we have for the conclusion, f is decreasing, but the curve is concave upward. Now as to x equal to -1, earlier we have that observed, okay, at the case of f prime of x equal to 0, and at x equal to -1, f double prime of x would be positive. That's -6 times -1. So what is this telling us about this particular critical point? With f double prime positive, it means the graph at x equal to -1 is concave up, and therefore that point of -1, 0, or -1, -2 is a minimum point. Now the interval x greater than -1 but less than 0 would render f prime of x positive, f double prime of x also positive. Conclusion is f in this interval is increasing, the function is increasing, and it is concave upward. At x equal to 0, y is 0, and f prime is 3. Now this is a point of inflection. This is the point at which f double prime is 0. So f has a point of inflection at 0, 0 with inflectional tangent slope of 3. Whenever x is greater than 0 but less than 1, f prime would be positive. Again, you can make use of a test value. You substitute in there and take note of the sign of each of these factors. So all the factors will be positive, and therefore the product of the three positive factors would be positive. But f double prime would be negative. So this will tell us that the function in this particular interval is increasing, but the graph is concave downward. At x equal to 1, y equal to 2, f prime is 0. So again, this is a critical point. And at this particular point, f double prime is negative. So the critical point is a maximum point. And for the region where x is greater than 1, you can verify that f prime would be negative. That will be the product of two positive factors with one negative factor. And f double prime would be negative, indicating that in this particular region, the function is decreasing, the graph of which is concave downward. So, based on the result, we now can sketch this graph. Take note that -1, -2 is a minimum point, +1, 2 is a maximum point, 0, 0 is a point of inflection, and that Whenever x is less than -1, concavity is upward. Between -1 and 0 is still concavity is upward. But between 0 and 1, the concavity of the graph is downward. Same with the portion where x is greater than 1. Okay, so with the result as given in the table, you would be able to sketch this curve. Take note that in the vicinity of the minimum point, concavity should be upward, and concavity changes at this point, 0, 0, because this is a point of inflection. And then to the right of this point, where we observe the maximum point, concavity is downward. So if we are dealing with a polynomial function, then we can neatly sketch the curve of the function by using the result of calculus-based analysis of its properties in terms of the maximum or the minimum point. These are points where y prime is 0, and the point is said to be maximum if y double prime value is negative at this point, and minimum if y double prime value is positive. This is using the second derivative test. Another property that we look into is locating the point of inflection, and this is or are points on the graph where y double prime is 0. Remember, the point of inflection is the point on the curve where we observe a change in the concavity of the graph.